One of the major topics in the chapter of ray optics is to do with concave mirrors. When we study about concave mirrors, we study about images formed by a concave mirror. You might have practiced drawing the ray diagrams when the object is placed beyond the center of curvature, then where is the image formed and what is the nature of the image. Then when the object is placed at center of curvature, between center of curvature and focal point, at focal point, and between focal point and the pole of the mirror. For all these positions, you might have very meticulously drawn the ray diagram, you might have followed a few rules to draw the ray diagrams, and you might have got a very clear-cut idea as to how the image is formed. So far is so good. But then, keeping the future in mind, would you be spending quite a lot of your time drawing the ray diagrams every time you want to figure out how an image is formed, where an image is formed, is the image diminished or is the image magnified? It's not a very correct approach, right? Robustically speaking or correctly speaking, you need to have a very good mathematical technique using which just by solving a bunch of equations, you should be able to figure out where the image is formed, what is the size of the image, is it upright or erect or is it inverted image. All this should be figured out just by plain mathematics, right? Not like drawing ray diagrams. Ray diagrams is a very good approach, but that is of a limited utility and it is time consuming. What I will show you now first is a ray diagram just to help you quickly recall how the image is formed, where is the image formed, what is the nature of the image for various object distances, and then come to mirror formula and then address the most important issue for this discussion, that is sign convention. Because if you are not able to understand the sign convention, then neither will you be able to give the inputs properly to the equation, nor will the output make any sense to you. Because if it is minus 20, you don't know why it is minus. If it is plus 30, you don't know why it is plus. Right? So we'll approach it step by step. First thing is looking at the ray diagram and a quick recall of how the images are formed. Here is a simple simulation for that. As you see, this is a concave mirror, and this is an object placed between the focal point and the pole of the mirror. And the ray diagram, I hope you are able to recall, a ray drawn parallel to the principal axis upon reflection passes through the focal point, right? A ray hitting the pole of the mirror is reflected back, making the same angle. These are the two reflected rays. Now the way we figure out as to where the image is formed or what is the nature of the image is, we look for the point where these two rays meet. There are two cases again. Either the rays will meet on their own. If they meet on their own, then you don't have to do anything. Therefore, we call it as a real image. It is really formed. You don't have to do anything for it. Whereas in some other cases, the rays don't converge towards each other, they diverge. It means they move away from each other. When they are moving away from each other, there is really no possibility of them meeting each other, right? So in that case, you have to do something more, like what we see here. You see, this ray is going along this line and this ray is going along this line. Is there any chance for these two diverging rays to meet anywhere here? Even if I extend this to infinity, there is no chance at all. Therefore, what we do is, we extend the ray backwards and these two lines happen to meet here. No, I am not saying rays because these are the dotted lines that we are drawing. These are certain, very fine points which if you start imbibing, you will understand physics better. Or let me put it this way, you will start hating physics less. Right? That is how it is nowadays. So this is a light ray, there is an arrow. This is a light ray, there is an arrow. Also notice that these are solid lines. This is an extension that we are making. So two changes to it. First, it is not a solid line, it is a dotted line. Second, there is no arrow here. Because drawing an arrow here is meaningless. Light is not traveling in that direction. So these two lines meet here and then we say this is an image formed. This image is definitely formed due to the dotted lines. Therefore, for valid reasons, it is called as a virtual image. You might have learnt all this. So for an object that is placed between focal point and the pole of the mirror, we see that an enlarged, erect, virtual image is formed. Now let us move this object even closer. You see, as I decrease the object distance, what is happening? The image is also coming closer and closer. So for lesser and lesser object distances, the image keeps on coming closer and closer to the mirror. But there is one thing that you can observe. You can bring it very close, always see that the size of the image is more than the size of the object. So this is how you learn lots of concepts. The virtual image formed by a concave mirror is always erect. It is always magnified. It means it is larger when compared to the object. Now let us pull the object back and see what happens. If I increase the object distance, you see, as the object is moving back, the image is also moving back. The image is moving back, and you see the magnification is increasing. Right? All this that you see using ray diagrams can be obtained using mathematics, and that is what we are going to do now. So as you keep on moving it back, you see the image is so far that it has gone beyond the screen. Now this again helps you, I hope, appreciate the utility of mathematics. Ray diagrams, really you would need 5-6 meters of a white sheet to draw all this. Is that possible? Whereas in mathematics, within 3 steps you can tell where the image is formed. That is what we are trying to look at. So you see, at this point, the rays neither meet here nor do they meet here. So this is where image is formed at infinity, right? But if I increase the object distance, now I'll come this side and you observe this, right? So for this object distance between focal point and the center of curvature, there is an enlarged inverted real image. You see, are we having to draw any dotted lines anywhere here? The rays are very nicely reflecting and they are themselves converging at one point. So if I further increase the object distance, as the object moves further, the image comes closer. In case of virtual image, it was different. When the object was coming closer, the image was also coming closer. Here, as the object is going further, the image is coming closer. You see, the object is moving far and the image is coming closer, and the image is getting reduced in size, and at center of curvature, here the object size is exactly equal to the image size. If I move it further, you see a diminished image is formed. It is smaller in size. And as it keeps moving closer and closer towards the object, you will get a smaller and a smaller and a smaller image. It becomes very small. Okay. So what we understand from this is, a concave mirror, can it produce a virtual image? Yes. And what is the quality? It will always be enlarged. Can it produce a real image? Yes. What is the quality? It can produce both an enlarged real image and a diminished real image also. All this can be handled by a single equation and a proper sign convention.